During this presentation, we'll look at how the changes taking place in the automotive world might affect braking systems and their components. We'll examine the key differences between today's cars and their predecessors, with a particular focus on what has changed over the years and what has remained basically the same. We'll then look at the leading trends relating to cars of the future, such as environmental sustainability, safety, and a different model of personal mobility from the one in place today. In part 2 of the presentation, we'll take a look at how these changes will affect the car's most important active safety component, its braking system. Finally, in part 3, we'll turn our attention to how these changes to cars and braking systems will affect the spare parts market. Let's start by looking at the differences that already exist between the cars of yesterday and the ones on sale today. To get a clear idea of what has changed over the years, let's take one of Europe's best-selling cars, the Golf, as an example. The first generation of the compact German hatchback was launched 45 years ago. To provide an example, we have taken 5 different models, all with similar-sized petrol engines, ranging from 1.4 to 1.6 liters, from the Mark I to the Mark VII Golf, which is the penultimate in the series. If we look at the technical specifications of the different models in the table, we can see that both the car's weight and its top speed have increased over the years, along with its engine power. This increase in weight and speed is by no means unique to the Golf. In fact, we could look at the evolution of the vast majority of cars over the past 40 years, and we would find the same kind of change. The increase in total weight, despite the use of lighter materials, is attributable to many factors, one of the most important of which is the increase in the car's overall dimensions. The Mark I Golf was much smaller than the Mark VII. The more extensive use of safety devices, such as side impact bars in the doors and multiple airbags, for example, is another factor. Finally, today's cars are equipped with an array of electronic devices that their predecessors obviously didn't have. The increase in vehicle weight and speed over the years has made it necessary to fit increasingly powerful braking systems in order to dissipate the kinetic energy and hence the heat generated during braking. Having looked at the aspects of car design that have changed over the years, let's now look at the aspects that have remained basically the same. Apart from their styling, dimensions, electronic equipment and safety devices, we can't help noticing on closer inspection that the main components of cars have remained largely unchanged. The car's brain is still the driver, who remains in charge of all the decision-making. Its heart is still an internal combustion engine, and its ability to move is still derived from its wheels. So in terms of their basic elements, cars have remained unchanged since their invention 130 years ago, and still essentially consist of wheels, a combustion engine, and a driver. So far, we have focused on the past and present motor cars. But what does the future have in store? The leading experts on the automotive industry all agree that in the years to come, cars will be subject to 3 key trends. Environmental sustainability, requiring reductions in emissions and the electrification of powertrains. Safety, based on increasingly advanced driver assistance systems. A new model of personal mobility shaped by a new generation of increasingly connected users who are becoming decreasingly less invested in the idea of cars and driving as a means to an end. In other words, drivers who are not interested in owning a car, but just want to use one when they need it. The younger generations are laying the foundations for pay-per-use mobility in place of private car ownership. Nearly 50% of Generation Y consumers use smartphone apps for travel purposes, and already plan their journeys in such a way as to maximize the time they have to get other things done. These are likely to be the trends of the near future, and not only will they affect the design of tomorrow's cars, they will also affect many of their components, including, to some extent, their braking systems. Certain changes in braking systems, in fact, can already be seen on some of today's cars. Starting with the subject on environmental sustainability, one of the key questions that all car manufacturers must tackle if they are to overcome the challenges of the future is how to reduce carbon dioxide emissions. Although not directly harmful to human health, CO2 emissions are responsible for the greenhouse effect. Reducing the carbon dioxide emissions of cars with conventional internal combustion engines means reducing their fuel consumption. Cutting fuel consumption, in turn, depends on the type of engine used and the weight of the vehicle. This is the reason behind shifting away from the trends of the past, and reducing vehicle weight is becoming increasingly important. And inside the vehicle, it is vitally important to reduce the weight of the braking system, because this forms part of a car's unsprung mass, so has a major effect on fuel consumption and handling. In this presentation, we'll take a look at some of the most significant technologies used to reduce the weight of brake discs, pads, and calipers. Some of these technologies have already been on the market for several years, while others are due to be launched in the near future. We'll look at composite and floating discs that use lighter materials on the hub, and even discs that use ultra-lightweight materials on the braking surface. We'll look at brake pads with fiberglass backing plate and a new brake caliper production process known as Brembo semi-solid metal forming. Starting with brake discs made of lightweight material, one of the first examples, which BMW uses on its premium vehicles, is the composite disc with cast iron braking surface and aluminum hub, mechanically joined with steel pins. This solution reduces weight by about 15% compared with an integral cast iron brake disc of the same size. Mercedes, meanwhile, has been using a different solution on all its higher-end models from the C-Class upwards since 2014. Mercedes uses a composite disc with a cast iron braking surface, interference fitted to a hub in very thin gauge steel. This solution, produced by Brembo as Mercedes' original equipment, reduces weight by about 15% compared with an integral cast iron brake disc. In terms of aftermarket parts, Brembo offers another solution that is fully interchangeable with the Mercedes lightweight discs and delivers the same advantages. This is the co-cast brake disc. Brembo's co-casting technology makes it possible to join a cast iron braking surface with a steel hub by co-casting the two materials. The end result is a brake disc that offers the same weight reduction as the original disc, that is about 15%, made with the same materials as the original Mercedes disc, specifically high-carbon cast iron and steel. In other words, we achieve exactly the same performance and appearance using different production technologies. Another very interesting solution that Brembo has in the pipeline, but has not launched yet, is the EcoCast brake disc. This is also a composite disc made by co-casting two materials. In this case, the materials are cast iron for the braking surface and aluminum for the hub. The advantages are the same as for the previous solutions. This solution is also ideally suited to medium and large premium cars. Now let's take a look at even higher performance cars, such as competition cars and the most sports-oriented versions of standard premium cars. Here, dual-cast discs are the most widely used technology for reducing brake disc weight. So far, we have looked at composite discs, consisting of two parts joined by pins, pressure, or co-casting, which do not allow any movement at all between the two parts. Dual-cast discs differ in this respect. They consist of two parts, a high-carbon cast iron braking surface and an aluminum hub, joined by co-casting. In addition to reducing weight by about 20% compared with a comparable integral brake disc, this also gives the system a certain elasticity, which significantly reduces the risk of deformation between the braking surface and the hub. The second-generation dual-cast brake disc has the same benefits and advantages as the first generation. The different position of the pins connecting the braking surface to the hub, they are now located on the top half of the braking surface, has improved brake disc ventilation, thus increasing the disc's heat dissipation capacity and resistance to thermal cracking. So this is an even higher performance solution, which is suitable for premium sports cars. On the subject of reducing both weight and possible deformation between the braking surface and the hub, mechanically connected floating discs certainly warrant a mention. These are high-carbon cast iron discs connected to an aluminum hub by means of elastic bushes, which join the two elements together, while also allowing for a degree of movement. This gives the system enough elasticity to ensure that it does not suffer permanent deformation, even at high temperatures, thus preventing unwanted vibration. This solution is also best suited to competition cars and high-end sports cars. Another highly innovative solution involves the use of composite discs with a steel hub, mechanically connected to a stainless steel braking surface. The use of steel, which has high mechanical strength, makes it possible to reduce the thickness of both the braking surface and the hub. Due to the limitations imposed by the production process, the braking surface cannot exceed a maximum thickness of 8 millimeters, whereas the hub is made using steel with a thickness of 2.5 millimeters. As the braking surface is made of stainless steel, it does not need to be painted and is not subject to rust during use. The hub, however, is painted. The braking surface can comfortably withstand temperatures of up to 600 degrees Celsius. The advantages of this highly innovative solution are that it weighs around 30% less than a cast iron brake disc. It increases the durability of the brake discs and brake pads, and it enhances the perceived quality of the product because it remains completely free from corrosion. Possible applications include the front and rear axles of ultra-lightweight vehicles, the rear axles of A and B segment vehicles, and the rear axles of C segment electric vehicles. The sheet steel hub is made by deep drawing. The holes and slots in the hub for connecting it to the braking surface are made by perforating. The braking surface production process involves cold punching stainless steel. This process also makes the holes in the braking surface. The process is followed by heat treatment and grinding. The final stage involves assembling the two components and carrying out final grinding of the hub surface to meet the required tolerances. Another effective way of reducing the weight of brake discs is to use integral aluminum discs reinforced with special components to increase their strength. The difficulty of this solution lies in the critical conditions to which the material is subjected to, such as temperatures in excess of 400 degrees Celsius. The design also involves using special brake pads for this type of material. The big advantage of using aluminum is that it can reduce the weight of the brake disc by around 40% compared with a similar cast iron disc. Ultra-lightweight vehicles are a possible application for this solution. Finally, no discussion of ultra-lightweight materials for brake discs would be complete without a mention of carbon ceramic discs. These are also floating brake discs, but instead of the traditional cast iron braking surface, they have a carbon ceramic braking surface. They offer numerous advantages in addition to reducing weight, which in this case can be as much as 50% less than the weight of a cast iron disc. The absence of thermal deformation, the high and constant friction coefficient, and the long durability of over 200,000 kilometers are all factors that make this the highest performance brake disc type currently on the market. Needless to say, Their use is confined to top-end sports cars from manufacturers like Ferrari, Porsche, Lamborghini, Aston Martin, etc. This graph shows all the different solutions adopted over the years to reduce the weight of brake discs. From floating discs, which have already been on the market for over 20 years, to the latest composite discs, all the way up to the latest technologies involving the use of reinforced aluminum and steel discs, offering huge reductions in the weight of the components. Until recently, these special components were only used on supercars and sports cars. The need to reduce emissions, however, has led to an interesting new development. Brake discs made with lighter materials are now appearing on more mainstream cars, which obviously account for a larger percentage of the market. We expect to see this trend continue into the future as manufacturers widen the use of increasingly sophisticated materials and technologies in order to produce lighter, higher performance components compared to those used in the past. This will clearly open up a major new opportunity for those players who manage to keep pace with changing requirements and have the skills, know-how, and technology not only to follow, but above all to shape these developments. Research aimed at reducing the weight of braking components is obviously not confined exclusively to brake discs, but involves other components of the braking system as well. The Libra project involves the use of a fiberglass backing plate for the brake pads instead of the normal metal backing plate. The backing plate is molded together with the friction material in a production process that differs considerably from the one currently used for producing brake pads. The use of fiberglass reduces the weight of the brake pad by about 30% compared to what you would get with a metal backing plate, while also reducing thermal conductivity and eliminating corrosion. Its lower resistance to thermomechanical stresses means this type of solution is best suited to use on the rear axles of electric cars, where regenerative braking results in decreasing use of the disc, lower operating temperatures, and lesser wear. Semi-solid metal forming is a process that makes it possible to produce aluminum brake calipers from secondary aluminum, originating from recycled aluminum, instead of primary aluminum, pure aluminum originating from the mining of bauxite and alloyed with another material to produce brake calipers. The design has a dual purpose: environmental, because it involves using recycled aluminum instead of mining new aluminum. This process also has a lower environmental impact in terms of energy consumption. By applying the process for secondary aluminum to primary aluminum, it is possible to produce brake calipers with higher mechanical specifications or lower weight, because this process yields lower thickness without compromising the mechanical strength of the material. Normally, secondary aluminum cannot be used in the production of brake calipers because the impurities in recycled material impair its mechanical properties. So in order to make it usable, Brembo has developed a new technological process in which secondary aluminum is melted at 650 degrees Celsius, instead of the 740 degrees used in conventional processes. At this lower temperature, the aluminum does not melt down fully into the liquid state, but remains in a semi-solid state, similar to the texture of butter as opposed to water, to give you an idea. At this point, the semi-solid composite is mixed and injected into a caliper mold. Once in the mold, this semi-solid material takes on a globular structure, which increases the mechanical strength of the caliper. Brembo is working on this new technology with primary aluminum so as to be able to produce lighter calipers while retaining the same mechanical strength. The weight saving that can be achieved with calipers made using this process is approximately 8%. As mentioned previously, in addition to reducing emissions by reducing vehicle weight, one of the goals of car manufacturers is to reduce particulate matter. Recent research has shown that the copper and other metals transferred to road surfaces as a result of brake pad wear becomes highly toxic to certain aquatic microorganisms once it finds its way into streams and rivers. Therefore, in 2010, the states of California and Washington have passed legislation that brake pads sold or fitted in both states must have lower levels of copper and other heavy metals. Although this regulation is currently confined to these two states only, manufacturers of cars and braking systems operate in a global market, so are preparing to limit the presence of copper in brake pad components. Under the Better Brake rules, in order to sell their products in California and Washington, friction material manufacturers are required to register their products, which can fall into three different categories depending on how much copper and hazardous metals they contain. With effect from 2025, only N-level brake pads with a copper content of less than 0.5% of the total weight of the friction material will be eligible for sale in these states. Still on the subject of brake pads, the Cobra project, which Brembo is involved in alongside a number of other companies in the area, is based on a new technology for the manufacture of brake pads that makes it possible to replace the phenolic resins used as binders with a new cement-based material. Alongside Brembo, this project benefits from the participation of the Mario Negri Institute, Italcementi, a leading manufacturer of construction materials, and Connecting Ambition, a multinational consulting company specializing in innovation and attracting public funding. Obtained by the reaction of phenol with formaldehyde, phenolic resins are used as paints and mastics because of their adherence. They harden on drying. Formaldehyde is a very volatile and hence very hazardous substance, as it can find its way into the human respiratory tract. The new cement-based materials are required to deliver equivalent performance to traditional materials. This means they need to meet the high performance standards expected of the most demanding sports applications, while minimizing their fine particulate emissions and environmental impact. The new process offers multiple advantages. Not only does it reduce the amount of fine particulate generated during braking, but it also saves a considerable amount of energy and water during production, and results in a product that can be used with both cast iron discs and steel discs. The compound has already been approved to ECE R90. Having looked at all the major aspects of reducing emissions and reducing brake dust, the final key topics that we need to cover in our discussion of new trends in the automotive world are electrification and autonomous driving. Although braking systems in today's cars are still based on a hydraulic circuit, they are now extensively connected with electronic systems of various types. Originally, these systems were designed simply to help control braking and became known as ABS. As they evolved, they started communicating with the braking system to help control vehicle stability as well, and became the first ESP systems. They then spawned a series of increasingly sophisticated systems for traction control, brake assistance, and brake force distribution. There is no longer any doubt that electric braking systems will be the next step after electronically controlled hydraulic systems. The Brembo brake-by-wire that we present here is a mixed system comprising electro-hydraulic brakes at the front and fully electric brakes at the rear. This combined system is suitable for vehicles with powerful front brakes that use fixed calipers, which are larger than floating calipers. Since they are larger, they leave no room for fitting any further electrical components, which are also quite large, on the front brake calipers. The system consists of a brake pedal with simulator, an electrical control unit for the front axle and one for the rear, two electromechanical calipers at the rear, and two hydraulic calipers at the front, controlled by two electric actuators. Let's take a closer look at the components and how they work. By pressing the brake pedal, we send an electrical impulse to two electrical control units, which distribute the impulse to the front and rear axles via electrical cables. So the brake servo, the brake master cylinder, and the brake pipes that send fluid to the calipers no longer exist. The driver still needs some pedal feel, however, and this is reproduced by means of a spring-loaded damper. One of the two control units contains general information about the vehicle's braking. On the basis of the type of pressure exerted on the pedal, the control unit translates the impulse into a braking torque for each wheel. Once the necessary braking force on each axle has been established, the control unit of each caliper sends the received impulse to the respective wheels. This control unit also enables us to modulate our braking differently between each of the two wheels when cornering. We have already established that because of the size and weight of a fixed caliper, not forgetting the greater mechanical complexity of the front axle compared with the rear, the solution for the front axle has a different configuration from the one for the rear. In this case, the electric motor, the control unit and actuator, are separate from the caliper and located near the wheel, but not on it. The electric motor therefore transmits force via a gear system and a crank connecting rod mechanism to multiply the pressure that sends it to the brake master cylinder, which in turn, via the brake fluid and the hydraulic circuit, transfers it to the caliper pistons. The front brake is therefore hydraulically actuated, even though its operation is started by an electrical control. As for the calipers, they are floating calipers which include an electric motor actuator. The calipers receive an impulse from the control unit, which is in turn received from the brake paddle. This impulse is then converted into a required brake force target based on the pressure exerted on the paddle. Once sent to the electric motor of the caliper, this impulse is converted into mechanical pressure on the cylinders and brake pads via gears and a screw, which converts the electric impulse into mechanical pressure. Using a separate electrical control from the one used for braking, the electric motor also applies and releases the parking brake. Brake-by-wire systems offer numerous advantages over conventional braking systems. Let's take a look at some of them. In terms of braking distance, brake-by-wire is better than current automatic braking systems. The driver can select different braking settings and can choose the pedal feel he or she prefers. The transition to regenerative braking takes place seamlessly and the driver's pedal feel is not affected. The brake-by-wire system also operates effectively in different and extreme temperature conditions. By optimizing the use of the brakes, the brake-by-wire system can reduce CO2 emissions. It also dispenses with a large number of hydraulic system components, thus reducing the need for maintenance operations compared with conventional systems. The brake-by-wire system can automatically adapt braking torque distribution as the load on the car varies. The adoption of brake-by-wire systems will also make it possible to change the design and ergonomics of cars. Since a series of components, such as the brake servo and master cylinder, are no longer needed, it becomes possible to redesign the vehicle chassis. It will probably be easier to achieve carryover too by simply changing the software. Thanks to a more flexible layout, it will also be possible to simplify production and assembly systems and improve the arrangement of space in car interiors. In conclusion, while a self-driving car with a hydraulic braking system is unimaginable, the brake-by-wire system can be shaped around all the needs of a Level 5 autonomous driving system. At the beginning of this presentation, we looked at how vehicle weight has risen continuously over the decades, and how recent years have seen an even more pressing need to reduce weight in order to reduce fuel consumption and hence harmful emissions. In this slide, we compare three models of the Mark 7 Golf with equivalent performance but different types of powertrain. We have one petrol model, which is the lightest but has high CO2 emissions, one hybrid model, and one all-electric model, which has almost zero CO2 emissions but weighs nearly 300 kilograms more than its petrol counterpart. This weight increase is mainly attributed to the considerable weight of the batteries, which also increases the thermal stress on the braking system. So the question is, Do braking systems need to be even more powerful than they already are because of the additional weight of batteries? Or is this offset by the fact that electric vehicles make significant use of regenerative braking and do not rely solely on traditional friction braking? In other words, how should the brakes of tomorrow be designed, and what criteria should they meet? The fact that hybrid and electric vehicles benefit from regenerative braking needs to be taken into account when establishing the design criteria. The presence of the regenerative brake means that the vehicle requires much lesser use of the traditional friction brake than a car with an internal combustion engine. In theory, therefore, braking systems can be downsized and made with smaller brake discs. Having said that, safety must be factored in. It is vital that the brakes deliver their maximum performance even without regenerative braking, because in certain conditions, regenerative braking is unable to work. The low noise of electric vehicles makes it even more important that no noise should come from the braking system. Comfort under braking has long been an important goal for manufacturers, and it will be even more important with electric vehicles. Eliminating residual torque is another necessity, which is even more important for electric vehicles than for cars with traditional powertrains. Residual torque in electric vehicles can compromise the energy balance of the system and hence the range. The fact that electric vehicles make less frequent use of friction brakes can lead to undue corrosion of the brake discs and pads. Furthermore, the friction coefficient must be stable even if the braking system has been left unused for long periods. It is therefore clear that brakes for electric vehicles require dedicated development, and this opens up considerable potential for innovation in the fields of corrosion prevention, friction materials, and lightweight design. In the final part of this training course, we'll take a look at the possible effects of these changes on the car and component market. Let's start by looking at the case of BMW and how its product range has evolved over the course of the company's history. Until 20 years ago, the BMW range did not exceed 8 models on the European market. Today, BMW has over 20 different models on the market with 40 different powertrains. The majority of manufacturers have followed a similar development pathway, and their product ranges have undoubtedly become much more complex and varied over the years. We're talking about a global market in which 98% of the cars on sale are still powered by internal combustion engines. Even now, hybrids and electric vehicles still account for only a tiny percentage of the world market. How much this will grow in the years to come is impossible to gauge, but all the indicators suggest that its growth will certainly be substantial, and this will lead to even more variety and a higher degree of model diversification than we already have today. As we've seen, the automotive market of tomorrow will be shaped by a wide range of factors. Firstly, environmental sustainability. New regulations will be put in place. Legislators will have far-reaching decisions to make, and certain emerging markets will make a major contribution to these decisions. New technologies, electrification, the strategic choices of manufacturers, and the presence of new players that joined the market only a few years ago. Lastly, a new generation of users, system connectivity, and the new levels achieved by autonomous driving technology. All these factors will affect the automotive market of tomorrow. On top of everything we've looked at so far, we're also aware that these changes may happen very quickly, similar to the latest changes in communication. Within a very short space of time, we've switched from landlines to smartphones, from paper to computers, from printed media to the internet, and from in-person communication to social media interaction, all in just under 15 years. What we've learned is that things change rapidly when a range of new technologies converge into new products. The companies and professionals operating in the industries concerned need to be ready not only to recognize change and follow it, but to use their know-how to shape it and reap the new opportunities that change always brings with it. That's why we believe that everything depends on knowledge. The knowledge and ability to develop the new technologies that the market needs, the ability to access data and information, the ability to offer new products and services, the willingness to embrace digital transformation and professionalization, and above all, the desire and ability to study and keep up to date in a constantly changing world.